Hello everyone, welcome to topic 9.10, electrolysis and Faraday's law. By the end of this, you should be able to calculate the amount of charge, flow, or current based on changes in the amounts of reactants and products in an electrochemical cell. We are going to introduce this equation, not cross it off. Way to go. Introduce this equation where I, because that's going to be the interesting one, is current. Q is charge. I'm checking because it's been a long day. Whoop, whoop, charge. And then T, generated from electrons flowing. And then T is time, because it's a lowercase t, not temperature. Okay, so current is defined as the amount of charge transferred over time, right? Charge divided by time. Charge divided by time. Because electrons are the carriers of charge, the current is therefore related to the amounts of reactants or products in an electrochemical cell through stoichiometric relationships. In essence, the goal of this topic is to apply stoichiometry to electrochemistry. Now, you might not be excited about that, but the original writers of this were. Some important pieces of information to know is that current is measured in amps or amperes. So 1 amp is 1 coulomb per second or per 1 second. Numbers are good to put in there. Faraday's constant, F, is a way to relate coulombs or the charge units to moles of electrons. And so that many coulombs is 1 for every 1 mole. These two relationships can be used in combination with our more typical stoichiometric relationships, so grams and moles and particles and all that fun stuff. Time, to answer questions about electrochemical cells. So like, how fast will the electrochemical cell die out? Or how long will it take to completely run itself to completion and reach equilibrium? So those questions can be answered using the two conversion factors above and our normal or previously covered stoichiometry relationships. So what mass of gold is plated by a 20-minute flow of a 5.5 amp current? So remember, this A is amperes, so this one. Okay, so we should, before we start, plot the conversions that are needed. So remember, maybe from your first year chemistry, you did a roadmap that told you what you started with. So we were given 20 minutes, so time, and then we were asked, hey, could you find the grams of gold that are going to be plated? And so then we connect all of these by conversion factors to change from one unit to the next. Okay, and so using that, we're going to look on the next page. So first you convert to seconds, so minutes to seconds here. And because we don't like to then put the equal sign and do a second conversion, we're going to tack on another conversion. So my minutes cancel. Now I'm going to put on and change to coulombs because it told me that it was 5.5 amps. And amps is the number of coulombs per 1 second. So I have 5.5 coulombs per 1 second. And so that cancels my seconds. Then I'm like, maybe I need to change my coulombs to moles of electrons because I can relate that to my reaction. And so I use Faraday's constant here. Sorry, I'm not reading the actual notes. I'm just walking through the math. So once we get to the moles of electrons by canceling using Faraday's constant, the amps provided in our seconds to minute relationship, we can then use the reaction to create a relationship between moles of electrons and the moles of gold. And we go back and we look at here, we see for every 1 gold, we need 3 moles of electrons. And so that gives us this reaction ratio. And that cancels out the moles of electrons. So going through and making sure we cancel stuff. Okay. Then we can go from moles of our gold in the reaction and cancel using molar mass because we were asked for grams of gold plated. So we'll look at the molar mass of gold. Then once we have all of this in, we do 20 times 60 times 5.5 and hitting the equal sign after each one. And you can do all the tops. So then times 196.96, then hit the equal sign, then divided by Faraday's constant, hit the equal sign, and divide by 3 because it's in the denominator. Make sure you're hitting that division mark. And it's 2 sig figs because we were given 20 minutes and 2 sig figs, as well as 5.5 amps. And so you end up with 4.5 grams of gold. Okay. So this, of course, can be used in other ways. So this is one example. You can also use it to predict the current needed in a reaction. For example, if you want to reduce 0.25 moles of copper ion to copper solid in 1 hour, what current would we need? So 1 hour, we change it to seconds because remember current or current is amps, so that is I is equal to Q charge over T. And the T is in seconds and the Q is in coulombs. And that gives me amps. When I have coulombs per second, that gives me amps or A, and that's my current. So I convert it to the time 1 hour to seconds. Then I change my moles and I change it to moles of electrons, then to coulombs. So this is my final conversion here. And I end up with a specific number of coulombs there. And then I divide by the 3,600 seconds to get 13 amps. Okay. So we have some pre-worked examples for us. Now let's take our turn and apply it to the I do and the we do. So calculate the charge transferred in a reaction that uses 2.5 amps for 5 minutes. Remember that this is I, and then 5 minutes is T. So that tells me I'm going to use, and then charge transferred is Q. So I is equal to Q over T. I'm going to rearrange the equation for Q. So I'm going to multiply both sides by T, and that cancels T out. So Q is equal to I times T, but my T needs to be in seconds. So I'm going to first take 5 minutes, and I'm going to convert it to seconds. So 60 seconds is 1 minute, and that is 300 seconds. So now since I have that, I can plug it into this equation where I is 2.5 amps. And if we remember that, that is coulombs per second. So I'm going to write coulombs over seconds. And I'm going to multiply that by my 300 seconds. So the seconds cancel out. And you should end up with 750 coulombs. It's funky algebra, guys. Don't forget your units though, because it's going to be a good way for you to check and make sure your units are working out, and so your math is being done correctly. So our we do. Tin is used as a cathode in the following chemical reaction given here. If 1.34 grams of tin is plated onto the electrode over 75 seconds, what current must have been used? So that's A. So we want to find A in the end, but in order to get there, we have to remember what A is, and that's coulombs per second. I know seconds, but I do not know coulombs. So let's map this out, our roadmap. We're first going to take grams of tin, which is Sn, and we should change that to moles of Sn. Since we are talking about current, the most logical choice to go to next is moles of electrons. Okay, so this is our molar mass conversion. Moles of tin to moles of electron is from our balanced equation. Then we can change moles of electrons to coulombs using Faraday's constant, because that has units of coulombs per mole of electron. So that relates those two. And then from there, and I'm going to put a little vertical line to tell myself that's where my conversion ends, but I can use the I equals Q over T to find my amps. Okay, so now let's set this up. So 1.34 grams of tin. And remember, your roadmap tells you what goes on top. So moles of tin. Then I'm going to go to moles of electrons, and finally go to coulombs. Okay, drag diagonal to cancel our units and to help us set up our conversion factor. And now we can plug in our conversion factor. So grams to moles is molar mass. So 1 mole of tin has 118.71 grams. You get that from the periodic table. Then from our balanced reaction, we see that for every 2 moles of electrons, we have 1 mole of tin. Then 1 mole of electrons has a charge of 96,485 coulombs. Remember, that is Faraday's constant. And when we run this math, 1.34 divided by 118 times 2 times Faraday's constant is 2,178 coulombs. We're not done yet because we are here. Now we're going to do this. So I is equal to Q, which this is my Q, 2,178 coulombs, over my time, which they told us 75 seconds. So then solving this, we end up with 29.0 coulombs per second, or 29.0 amps. And that is all you do. Okay, I say it is all you do. It is a lot of stoichiometry. So let's get practicing on this again and get used to using it. Make sure you are paying attention to your units. So complete the you do using the stoichiometry examples for this that we just went over. Check your work, and thank you for tuning in.